Good morning, everybody. First of all, to anybody in the United States, happy Veterans Day. That was just a couple days ago. So yeah, if you served in the military, thank you very much for your service. It's very much appreciated. And that's what the beautiful U.S. flag in the background is for. A little seasonal. Additionally, we have a new surprise for today. We have, we've got this. Spoiler alert. We also have this scene, which has right here, we have my paper. So when I do work on paper, since this is a Div 1 round, you'll be able to see what I'm doing. And then when I'm typing, my keyboard will be here, so you'll be able to see me type if you find that interesting. And then that'll be like this. So you'll be able to see both if you'd like. And when I'm just working on paper, I'll try and do the other. But yeah, we've got a Codeforces Div 1 round ready to go. We're going to be doing it in Java here. And we've got Eclipse ready. We should be good to go here. We've got A, B, and C with caps locked off. And here we go. Here's the contest. All right. So commentary is going to be in the lighter side, but solutions to everything I know how to solve will be at the end of the video. And you can watch it as we go. All right. Two integers. So we have two arrays, A and B. We have a transformation of array A. So choose an integer k. Choose k distinct indices. Add 1 to each of these. Permute the elements of A. Okay. Is it possible to perform some transformation on A so the resulting array is equal to B? So this example, the answer is yes. This example, they differ by 2, so the answer is no. Do we want to sort both of them? Yeah, the smallest things need to be equal or off by 1. If they're off by 1, we might as well have them match. So sort both and see if they differ by 1 in each position. I think that's fine. So if we are less than b at I minus 1, or 8i is greater than b at I, then works equals false. This out works if it does work, yes, otherwise no. I think this should be fun. Don't know what that delay was about. Okay, looks like we're good there. Interactive problem. So jury has a sequence A of length n such that A of I is equal to I. The jury chooses 3 integers I, j, and k. So these are 2 integers less than k. Oh, so 3 ascending integers. Okay. And the first 2 differ by at least 1. After that, the jury reversed subsegments I to j minus 1 and j minus 1 to k of the sequence A. Reversing the subsegment of the sequence A means reversing the order, yes. Yeah, I think I understand. So you've got like 2 things, you swap them, all right. You're given a number n, and you should choose to find I, j, and k after asking some questions. Okay. In one question, we can choose integers L and R asked the number of inversions of the subsequence. We're given the number of pairs. We're given the number of pairs of inversions, okay, in A. Are we given the new array? Oh, initially it's just in order. Okay, so you have a sequence, you do some inversions, and then we want to know how many inversions are there. And it's 10 to the 9. Oh, that's kind of annoying. All right. So we need we have log n plus 10 queries. Okay, so this is I, this is J, and this is K. So if we find, well, we can know the total number of inversions. And this is a sum of two squares. And then I guess we want to binary search when the first. Oh, if we know what if we know the last element? Yeah, this will tell us what the second square is. So if we see a 4 here, then we know this, so we know what this is. Yeah, in total this is 3 times 4 plus 3 times 2, 3 times 4 over 2, n times n plus 1 over 2, so how do we go backwards? So this means n squared plus n over 2 equals sum. So n squared plus n equals 2 times sum. So n squared plus n plus or minus 2 times sum, 0. Okay, this is x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. 1 plus or minus the square root of b squared 1 minus, or okay, so 1 plus (16) times sum divided by 2a. This is a square number? What the heck? I guess we can just binary search. That's fine. Okay, so yeah, we should be fine there, I think. A little annoying to implement, but it's fine. Okay, 4 solves, it's not too bad. Kusaga, you legend. Okay, let's go with B though. A multi-test case, that's kind of annoying. Okay, so we need the endpoints of this thing. So int L is this, R is this. No, what am I doing? So long total inversions equals query from 0 to n minus 1. Okay, so now we need to get the last. So the min will be 0, and then the max will be n minus 1. So while min is not equal to max, if query from 0 to need a mid, if this equals total inversions, then what do? If this is the total inversions, then this is good. So then max equals mid, otherwise min equals mid plus 1. Okay, so now we have the last element. So in last, or like long without last equals query from 0. Do these have to be less? Okay, they can be equal. From 0 to min plus or min minus 1. Okay, so then this is last will be total inversions minus without last. So then long second size will be last times last plus 1 over 2. Okay. Our second, like, total. So this is, I guess, just second size. So second total is this. And then first total equals total inversions minus the second total. And then we need first size, so static long n choose k inverse. We need long. Okay, so do this. We'll do this in a minute. So long first size will be n choose k inverse for the first total. And then we have our answer, I think. Yeah. So print exclamation point here. All right, and then we solve the next case. Okay. So first total, first size. Yeah, so then, okay, so then long k equals min minus 1. Oh, equals just the min. It's the last element that gets inverted. Long j equals min minus first size plus 1. Long I equals j minus second size. Print answer ijk. Okay, so if mid plus mid, or mid times mid plus 1 over 2 is equal to total, return mid. Otherwise, if this is greater than total, then max equals mid minus 1. Else min equals min plus 1. Okay, so we should be fine there. We then choose K inverse. Yeah, I think we're good. Okay, so let's do an example. 1, 2, 3, 4, 5. So let's say we make this I, this J, this K, 6, 7, I guess. Then we have 1, 3, 2, 5, 4, 6, 7. This is wrong. So the second size is this plus 1. This is this minus 1. Yeah. And these are both minus 1. Okay. I think we're fine here. Right. So we'll have one test case, n is equal to 7. 1 to 7. We have just two inversions. 1 to 4. We have just the one inversion. 1 to 6. 2 inversions. 1 to 5. We have 2 inversions. 1 to 4. We have just the one inversion. So they pick 2, 4, and 5. Looks right. Okay. Let's try submitting. Wrong answer, pretest 1.
Problem without wrong answer, test 1, sir.
We print 1, 4, and 5. What is this? So n equals 5, 2, 4, 5. Okay, not everything's being reset, right? Shouldn't matter. Oh, is this overflow? Nothing should overflow. Okay, so let's double check this example. So we have 1, 2, 3, 4, 5 initially. And then this is I, this is J, this is K. So we have 1, 3, 2, 5, 4. One to 5, we have 2 inversions. 1 to 3, the 1 inversion. 1 to 4, we have the 1 inversion. 1 to 4, we still have that 1 inversion. 2, 4, 5. Oh, so okay. 1, 3, 5 is what's wrong. So it's 3, 2, 1, 5, 4. One, 5, 1 to 5. So we have 1, 2, 3, 4 inversions total. 1 to 3, we have 1, 2, 3 total. 1 to 4, we have 3 as well. 4, we still have 3. 1, 2, 3. But it's 1, 4, 5. Okay, so second size is 2. And then min equals 5 or 4, I guess. J equals this minus first size minus second size.
Wrong answer is 0.
Okay, not terrible. Let's move on here. Well, actually, how are we looking? Yeah, so Kusaga is a genius, but other than that, we'll go to this NIM game, huh? What do you say? All right. Bob decided to take a break from his calculus homework and design a game for himself. The game is played on a sequence of piles of stones, which can be described with a sequence of integers s1 to sk, where si is the number of stones in the ith pile. Yeah, okay. On a turn, Bob picks a pair of non-empty adjacent piles and takes 1 stone from each. If a pile becomes empty, its adjacent piles do not become adjacent. Okay. The game ends when Bob can't make turns anymore. Okay, on a turn, Bob picks a pair of non-empty adjacent piles, takes 1 stone from each. Things don't become adjacent. Okay, the game ends when Bob can't make any more turns. Bob considers himself a winner if at the end all piles are empty. We consider a sequence winning if Bob can start with it and win with some sequence of moves. Okay, so yeah, if you can do the sequence and still win. You're given a sequence A1 to N. Count the number of subsegments of A that describe a winning sequence of piles. In other words, find the number of segments such that this is winning. Okay, so very obvious question 1. What is winning? Do we care? Yes, we care. So what sort of property are we looking for in this array? So we have some piles. You can't have a decrease here. So this has got to be at least an increase. This has got to be like same or decrease. The sum has to be even, because you remove 2 every turn. Anything else that's obvious? Nothing can be bigger than its neighbors. They're all true statements. Is this, if that's the case, is this always true? No, it's not, because you can have like 1, 2, 1, 2, 1. Yeah, this doesn't work. Well, the sum is wrong, but it also just doesn't work. You need the same parity of the same sum on even indices as odd indices. because every turn you affect an even and an odd index. I still don't think this is enough, because you can have something like 1, 0, 0, 1. Okay, this breaks rule 2. Does break rule 2. Wait, so what's the question? Oh, so we're not, okay. I misunderstood what the problem was. This might actually be like not, okay. Yeah, I thought you like have some sequence of moves you take from it and then, gotcha, okay. Okay. Yeah, I thought it's like take one from these two and then one from these two and then one from these two, and those are like the moves, and then it's like of these moves take a subsequence of those. But that would be probably pretty hard. This one is just like of the piles. Much easier problem. Okay. So this is still impossible because of this. Can we write a brute forcer? We can pretty easily write a brute forcer. Just to check this. Yeah, so just check, is something winnable? We can just do the greedy. Yeah. So, might not hurt to have it. All right, so yeah, we can do this, and then we can say yeah, so the sum is even, nothing's bigger than the neighbors, and okay. So yeah, this is pretty easy. So 8i plus equals, or S1 plus equals 8i. Okay, so this will also check that the sum is even, and then so let's just check this real quick. from interarray A to new interarray 1 plus r dot next int 5 6 and 4 int equals 0, else then a dot length I plus a dot equals 1 plus r dot next int 5. If check dumb a is not equal to is winnable at a, zero null. Okay, 352. Oh, yeah, this is not true. This goes from 1 to n. One, 1, 4, 3. So these add up to 5. These add up to 5, yeah. Should work. So we're breaking is winnable. Do. 4, 3, 3, 4. Okay, that is indeed not possible. Wait, no, so this should be 0, from 0 to n. I'm bigger than, yeah. This is 100% possible. Why is winnable returning false? Oh, wow. Okay. So this is right, okay. So, cool. Okay, so we want even sum equals odd sum. And then we want, what's this other check? Nothing bigger than neighbors. That's the check. Seems like a very doable problem. We'll get it. Yeah, so how do you do this? Shouldn't be too bad. We'll have some prefix sum. Ooh, what do we want? I guess you want the difference, right? Yeah, you want even minus odd. Yes, this might be kind of boring. So, yeah. So you've got, like, so we've got some value. And then what can happen? So this thing might be illegal forever. It might be an illegal start. Or it might be just an illegal end. So whether it's an illegal start determines does it get added. Whether it's illegal forever determines do we clear. And then whether this is an illegal end, do we add? Otherwise it's legal forever. Yeah. I think this should be easy. Okay, so this is no longer important. We have multi-test case, yeah. That equals this. What is the second number? Oh, that's just, okay. How big do the things go? Up to 10 to the 9? Are we gonna get roasted by Java for using a hash map? Good lord, that would be miserable. Can you imagine? Oh, we should make it a tree map. So that when the clear does something, it actually works. Okay. Yeah. So first check if it's illegal always. This val r equals I equals n minus 1 if it is 0, otherwise a I minus or a I plus 1. So we have the thing to the left and the right of us. If a I is greater than val l plus val r, then we are illegal always. So map.clear, nothing else is reachable, and continue. Yeah, okay. Otherwise, if we are 0, then we can counter self. If a I is equal to 0, then a is plus plus. All right. Otherwise, you can't ever just be yourself. You can't ever be yourself. Look at me. Discouraging people from being unique. I'm a terrible influence. No, I think I'm a decent influence. Anyway. Maybe, who knows? Jury's out. So yeah. So we also need like a long even minus odd sum. Okay, so in this case, even minus odd sum plus equals I mod 2. That's equal to 0, 1, otherwise minus 1. Okay, this times ai. So now we have this sum. All right. This needs to be a long. Add long to integer, sure. Okay, so count earlier matches. In this case, map, or so this is ans plus equals map.get emo sum. Even minus odd sum. So the things with the same even minus odd prefix. This is prefix not including us though. Okay. Yeah, that's what we'll put in the hash map, the old emo sum. Okay. So yeah. So if a at I is greater than or equal to a at I minus 1, then do this. Or less than or equal to, yeah, less than or equal to 0, and yeah, okay. This needs to be get or default, and 0 by default. Okay, so then if I is not equal to n minus 1 and a at I is greater than or equal to a at I plus 1, then we're legal start. Okay, so now map.put the old emo sum 1 plus map.get or default old emo sum or 0. I think this is it. No. This one. I'm missing something for this. Okay. Thank you for the good data. How does that pass? Wow, that's like way wrong. Okay. Yeah, so this should be fine. I think this should be fine. If we TLE, I will lose it. Oh my goodness. Oh my goodness. Dude, okay, I'm mad about the wrong answer, but also, what the heck is this? What the heck? All right, wrong answer, huh? Okay, so just generate some data. Find a break case. Probably. Oh no, am I overflowing somewhere? Ants is a long. Getter default should be long, that's fine. Yeah, it should be fine. Oh, test cases. How many test cases? Okay, yeah. So we need print writer. That's kind of my bad. Okay. Let's do this. Let's say we've got this. Okay, so we have some stuff here. This should be fine. Why is this not compiling? Import random. All right, so we have this random array. Now we just need to check it. So long df ans equals 0. New int array. J minus I plus 1. All right, and then we say if check dum of temp, then df ans plus plus. Really? What the heck? This thing? Oh. Yeah, I think this is fine. This times this plus 1 over 2. Yeah, that's right. Really, I'm wrong? Why would I be wrong? Wrong showing answer pretest 6. Because you've got the possibility of, yeah, I think this still just isn't right. You've got 1, 2, 1, 2, 1, 0, 0, and then the same thing in reverse. Yeah, this just isn't right. How did the brute forcer not find that? Okay, so it is wrong. So what character, back to the drawing board, I guess, with some more paper. So we still need this even and odd sum thing. We have the, yeah, we have this thing. So 1, 2, 1, 2, 1. I don't know if there's like, if you can hear this noise, but it's like someone is like asking a horde of elephants to move some furniture in and out of the apartment above me for like 20 minutes. So apologies there. I don't really know what I can do. Yeah, so what's up here? So we have like this sum is 4 and then it was 3 here. Like it gets negative. What if you like add 1 to everything here? Does that still break it? fixes it. Why is that? Why is that? Why is that? It becomes winnable? That's wacky. Why would that be? Feel like this, and then like this. Oh, because it's 2, 3, 2, 3, 2. Yeah, so like just 2, 3. Yeah, 2, 3, 2 is solvable. Okay, so we still don't have a good idea of when something is solvable. So you have, like when you do this naively, you do something like you have a count minus equals the next thing. Yeah, is it the differences that are important? So okay, after this turns into a 1, because there's a 1 difference. Now you take the difference, which is what you have next. So the difference, this leaves 0. Then you have this difference, so you have 2. You can't ever have negative. Now you have a negative minus 1, so it's impossible. Okay, so this is going to turn into something with a segment tree. So let's see this. So it's 1, and then you have a 2. So this is 2 minus 1. This is 1. So this is 1 minus 2 plus 1. Yeah, okay, so I guess let's go to this case. This is 12. 1, 2, 1, 2, 1, 0, 0, 1, 2, 1, 2, 1. Okay, so we have broken it. Good. Yeah, so the entire thing is what we're miscounting. Okay. So yeah, I guess what exactly are we looking for? We have, it's like 1, and then we have 2 minus 1. Okay, and then you have one minus 2 plus 1. So flip old sum and then add yourself. This needs to be positive. So we have 1 minus 1, 0, minus 2, minus 1, 0, or minus 1, minus 1, minus 2, 0, minus 1. And we have a 2, which is positive, so 1 and then 0. What if we put 2 1s here? this works. This works. This works. This works. This works. And there's one more that works. Which one works? Oh, this one. But the entire group does not. So the question is why? Yeah, we're not doing great here. Do you read D? We're given n strings, each of lowercase and uppercase English letters. In addition, it's guaranteed that a character occurs in each string at most twice. Ooh, so they're small. Find the longest common subsequence of these strings. Ooh. Ooh. We're given n strings. Okay, find the longest common subsequence. How many characters are there? 50? So these are at most 100 long. Maybe let's take a break from this for a while. Yeah, so they're about 100. We have 26, yeah, so 100 worst case. We can do something like dp at mask. What if they each contained every number at most once? Then it's just a permutation. Then either like take the number 1 or don't. I don't know. What if we just like hash the state? We have 10 integers up to 100. 100 to the 10th equals 10 to the 20. So 10 to the 20 possible states, which is a lot, but not that many. There are a bunch of restrictions, though. The last number for everything is the same. Right? Yeah. The last one for everyone is always the same. I don't know, maybe it works? I'm not sure. C seems easier. So why is this, yeah, what's going on here? Why is 1, 2, 1? Oh, because you can subtract 1 from everything. Probably, right? No, it doesn't work. Yeah, subtracting 1 from everything is... Or is it? You can always add 1 to everything. But adding 1 to everything might make it possible. Yeah, so you can't, the argument of subtract 1 from everything that works is not legit, because it makes it harder. Because this pair is never taken. So at this point here, this becomes impossible. So now we see a 2. So this goes to -2. This becomes impossible. Or it's still possible. Yeah, it's still possible. It's with this 1 that things become impossible. so this is like very annoying. Let's clean all this up. Okay, so yeah, so we can get this problem this fine. Let me get some water though, because I'm thirsty, but it's very doable. Okay. What is this going to be? It's going to be both of them? And also map upper. Yeah, I think so. Why not? Should be fine. Yeah. So tree map long to integer map equals imod 2 is equal to 0 lower, otherwise upper. Lure. Okay, so yeah, we've got this, so we got ourselves two. Either way, so if I mod 2 equals 0, okay, if I mod 2 equals 0, 0. Floor key or die. First key not equal to null, and map lower. Oh, is this going to be the last? Probably. Zero, 1, 2, 3, 4. Oh, this is the last. And this should be first. Okay, print writer. This is very sketchy because I don't really know why it's right. Okay. Yeah, so what is going on here? Okay. I guess what if we put a 0 in front of it? Got it. Easy to check. Okay, so simple version. Oh, wait. Yeah, that's fine. Yeah. So we need to remove this and then everything earlier. Left. Okay. Do I think we can get it? This is just like very annoying. And there's definitely a way of actually understanding what's going on here other than just getting it to work. We have to like remove everything after this. Yeah, so what's happening is when we increase to 1, this means yeah, so this means we're below other things. Yeah, okay, so we'll have okay, so we have these two things, and then in this first case, yeah, added to lower at I equals demo sum. So we're modifying this to I. This is the same thing, but for upper. All right, sounds good. Okay, so we have the lower and the upper. Yeah. Okay. So int index equals oh, so this should be a long. Okay, otherwise, so if yeah, what is this? Clear end. So if added to lower clear end is not equal to -1, then clear end plus plus. Map lower dot put. If it's not equal to -1, do this. Yeah. Okay, this is like almost right, I think. So this is less than clear OE and clear index lower. And a clear index upper. Okay, what's going on here? Null pointer exception. What is going on here? What is going on? come on. Okay, so this is to remove, to remove. Oh wait, this does just need to be one variable. Yep, okay. 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 Finally. Should be good to go. Good to go. All right, let's check this. Let's check this. 10. Okay, comment out this part and cross our fingers we don't TLE. Please don't TLE. Please don't TLE.
Problems, you got wrong answer, test 6, sir.
Ugh, for real? Okay. Why is that? Might we be removing ourselves when we shouldn't be? Yeah, I think that's fine. I don't know, this seems pretty close actually. Wait. Why are we deleting the even indices? So when we have, yeah, in this case, why are we deleting this? Ah, here. Oh. Yeah. It isn't. These zeros are weird. I think the zeros are what's destroying me. Does the array have zeros in it? Probably. That's why what I'm getting wrong. If only it didn't have zeros. Okay. 10 minutes left. Ugh. So it can look like this. Or it can look like this. Both of these are okay. The thing that isn't okay is yeah, this part is probably pretty arbitrary. Yeah, that's the problem. The zeros and ones shenanigans. Yeah, it's hard. It's a hard problem. So the idea is like, if you look at every other position, it's got to make a mountain sort of thing. It's got to be valid. If you look at only the even positions. But it can be of even or odd length. Yeah. Is this valid? Probably not. Or I guess it should be, right? Yeah, this is valid. So this is 1, 0, 2, 2, 1. So it's not valid because this destroys this, maybe? Wait, this doesn't make sense. This should be in a different direction. Yeah, you can't have two ups here. The parity's wrong. Yeah, so you can have so this is okay. Oof, that's hard. All right. Yeah. Okay. Well, I didn't get it. It's unfortunate. How's my rating gonna be? -88? Yeah. I guess that's all right. It's a little unfortunate, but that's fine. We can earn it back. Not the end of the world. Yeah, so I guess I didn't like prove my solution and then went, I don't know, maybe I was just wrong with it. Could have gone better. Ooh, Brandon, yikes. Yes, this is a bit tricky, I think. That's fine. Maybe I should have spent time on D instead. It's hard to tell. I guess hindsight's 20/20, right? But yeah, that's fine. So this is, I think this is called caret, this extension, which tells me this. I used to use CF predictor, and then apparently it was sketchy. And the nice part here is this tells you like what your expected rating is if you want to improve to the next one, the next rank. So it's kind of helpful. But yeah, I guess that's the idea. So we can go over A and B. They'll be pretty quick, but I can talk about them real quick. So the idea for A is that if you have the two arrays, you can sort both of them, and then because like you get a permute B, right? So the index the index that each element maps to in the other array is just the same thing as what it would be if it was sorted. So if you sort them, then the new index 1 maps to the old index 1, new index 2 to the old index 2, and so on. So you just need to make sure that you can change that array to the new B. And that's pretty easy. You just check to make sure each A is either equal to that B or one less than that B. And you can show that that works, but it seems somewhat clear to me that that's legit. And then for B is kind of cool. I can talk about it real quick here on paper. So the idea is that the number of inversions in something, like let's say you have some positions like this. If you invert these four, then every pair within here will be an inversion. So you have 4 elements, which means there will be 4 times 4 times 3 over 2 inversions. Every node has an inversion with every other node, and then you counted each edge twice, so 4 times 3 over 2. So that's how many inversions there are for a set of 4. And this is equal to like 1 plus 2 plus 3. So an easy way of like imagining what this would be like if we have these two ranges that both get flipped is we have 0 plus 1 plus 2 plus 3, and then we have plus 0 plus 1 plus 2. So this is the total number of inversions. And we can like use this pretty easily. So if we know what this last number is, we can figure out how big this range is. So what we're going to do is binary search for this last number. Then once we know how big this range is, we can figure out how big this range is because we know the sum of these elements. We can get the sum of everything in just one query. So we know the sum of everything, then we know the sum of these elements here, and we know the sum of these, and we know what this last element is. So we're doing one binary search for this. We do one query for everything, and then I guess we do one more query for what this element is. In particular, in order to get this element, we can query everything, and then if we know what this element is, we query everything but that from the beginning. And that will give us the 0, 1, 2, 3 plus 0 plus 1, so we can figure out this is a 2. And then we know how big this first range is, and then we can figure out how big this is by saying, well, we know it's going to be a sum of, like, it's going to be some formula that looks like this, n times n minus 1 over 2. So what is n? You can binary search that. I'll show you the code for both real quick here. There's code for A, very quick. Sorry, hang on. Yeah, there's code for A and code for B. Yeah, code for A, you just sort them and then check. For B, I've got this query method, which is helpful. And then this is to binary search to see for a given n choose 2, what is the n? Yeah, and then I just do what I mentioned earlier as I described it. C is a bit tricky. Yeah, I have like a rough idea, but like there are a couple observations. Yeah, I guess it's not solid enough that an explanation would be helpful in solving the problem. So good luck on that, I guess. And hopefully you did well in the contest. It was a little bit of an unusual time, but still a fun contest. Problems A, B, and C were all good. I can't complain about the problems. I didn't do too well, but you know, you win some, you lose some. And this one's, I guess, one we lost. That's fine. We can come back fighting in the next one. As far as road to LGM, we're pretty much where we were before, roughly the same distance to go, I think. We're gonna be about 2,500, so that's fine. Small elo hit, but yeah, we learned, and I'll upsolve and get better from that. All right, thank you for watching. Hopefully you enjoyed the contest, and have a great day. Goodbye.